6. The second law of thermodynamics. Welcome to one of the most important chapters in thermodynamics, the second law. This is where things start to get more exciting because we move beyond just energy conservation and start talking about direction, why some processes happen naturally and others don't. Think about this. When you drop a glass, it shatters, but you never see it come back together. That's not because it breaks the first law of thermodynamics, but because of the second law. It explains why energy always flows from hot to cold, why engines can't be 100% efficient, and why time seems to move in only one direction. In this chapter, we'll explore simple concepts like heat engines, refrigerators, and entropy. Don't worry, we'll go step by step using real-life examples. By the end, you'll have a clear understanding of how energy behaves in the real world, beyond just numbers and equations.
1. Introduction to the second law. Let's talk about why the second law of thermodynamics is a big deal. The first law simply tells us that energy is conserved. You can't create or destroy energy. But that's not enough to explain real life. In real life, things only happen in one direction. Your coffee cools down, but it never gets hot by itself. This is where the second law comes in. It explains why some processes happen naturally and others don't. It introduces the idea of energy quality, meaning not all energy is equally useful. It also tells us which processes are valid and sets a ceiling, the theoretical limits, on how efficient systems like engines or refrigerators can ever be. Think of it like this. The first law tells you the total money you have, but the second law tells you how much of it you can actually spend. Understanding this law means you understand the natural direction of processes in the world around you.
2. Thermal energy reservoirs. Now let's talk about thermal energy reservoirs, which are key players in thermodynamics. Think of them like massive heat banks. Large bodies that can absorb or release heat without really changing their own temperature. This is why oceans, rivers, and even the atmosphere stay relatively stable despite constant heat exchanges. We break them down into two types. First, heat sources. These are like the sun or a furnace, always supplying heat. Second, heat sinks. These act like giant sponges, soaking up heat, like the ocean absorbing industrial waste heat. But there's a catch. If we dump too much heat into the environment, we cause thermal pollution. This overheats ecosystems, harms aquatic life, and disrupts the natural balance. That's why engineers always pay attention to how much heat gets released back to nature.
3. Heat engines. Let's explore how heat engines work. A heat engine takes heat and turns some of it into work, but never all of it. There are always limits. This is why no car or power plant is 100% efficient. Heat engines follow 4 simple steps. First, they get heat from something hot, like fuel combustion. Second, they convert some of that heat into useful work, like moving a car. Third, they must release leftover heat to something cooler, like the environment. And finally, they work in a cycle, repeating this process over and over. To measure their performance, we use thermal efficiency, which compares how much useful work we get out versus how much heat we put in. The equation shows why we can't avoid waste heat. There will always be some energy going to the cold side, which is why thermal pollution happens and why energy efficiency is so important in engineering.
4. Refrigerators and heat pumps. Let's make sense of refrigerators and heat pumps. These devices don't create cold or heat out of nowhere. They simply move heat from a cold place to a hot place, which is the opposite of how heat naturally flows. A refrigerator pulls heat out of your food and pushes it into your kitchen air. That's why the back of your fridge feels warm. A heat pump does the opposite during winter, pulling heat from cold outdoor air and moving it into your warm house. To measure how good they are, we use something called coefficient of performance, or COP.
For refrigerators, COP tells you how much heat you remove per unit of work. For heat pumps, COP tells you how much heat you can add to a space per unit of work, and it's always just the refrigerator's COP plus 1. This is why heat pumps are surprisingly efficient when used properly.
5. Perpetual motion machines. Let's talk about perpetual motion machines, something that sounds exciting but is actually impossible. There are two types you'll hear about in thermodynamics. The first is PMM1, which breaks the first law of thermodynamics. It claims to create energy from nothing, like a machine that keeps running without fuel. Sounds nice, but it's impossible because energy can't just appear out of nowhere. The second is PMM2, which breaks the second law. It claims to convert heat entirely into work with 100% efficiency, meaning no waste heat, no energy loss. Again, this goes against nature's rules. There's always some waste when we convert heat into useful work. In simple terms, PMM1 cheats energy conservation, and PMM2 cheats energy direction and efficiency. Both are fun in science fiction, but completely forbidden by physics.
6. Reversible and irreversible processes. Let's break down one of the most practical ideas in thermodynamics: reversible and irreversible processes. A reversible process is like a perfect magic trick. If you rewind it, everything goes back to exactly how it was, with no trace left behind. In real life, though, most processes are irreversible. You can't unburn a match, unmix cream from coffee, or unscramble an egg. Irreversible processes always leave some footprint behind. Some energy gets wasted, usually as heat. Why does irreversibility happen? Common reasons are friction, free expansion, heat moving across temperature gaps, substances getting mixed, and chemical reactions. These factors make real engines, fridges, and machines less than perfect. Understanding these sources helps engineers design systems that minimize losses and perform closer to ideal.
7. The Carnot cycle. Now we come to the gold standard of thermodynamics, the Carnot cycle. This is the most efficient cycle you can ever get between two temperatures. No real engine can beat it. It's like nature's upper limit. The Carnot cycle runs through 4 perfectly reversible processes. It starts with isothermal expansion. Heat comes in at high temperature while the system expands. Then adiabatic expansion cools it down further without heat transfer. Next comes isothermal compression. Heat leaves at low temperature while the system compresses. Finally, adiabatic compression warms it back up to the starting point. Why does this matter? Because the Carnot cycle defines the best efficiency any engine can achieve. It's a reference point, like comparing your running speed to the world record holder. Real machines always perform worse, but understanding Carnot helps engineers figure out how close they can get to perfection.
8. The Carnot principles. Let's look at 2 simple but powerful Carnot principles that every engineer must know. The first principle says no engine, no matter how advanced, can be more efficient than a reversible engine working between the same 2 temperature limits. In other words, the Carnot cycle sets the absolute ceiling for efficiency. The second principle adds to that. If you have multiple reversible engines working between the same 2 temperatures, they all perform exactly the same. It doesn't matter how they are designed, their efficiency is identical. These 2 rules give us a baseline to judge all real machines. If any design claims to be more efficient than a Carnot cycle, it's a scam. These principles help engineers stay grounded in physical reality and avoid chasing impossible dreams.
9. The thermodynamic temperature scale. Let's talk about how we actually measure temperature in thermodynamics. Instead of using arbitrary numbers like Celsius or Fahrenheit, scientists developed a scale based on how heat engines behave. using only physics, not physical materials like mercury or alcohol. With reversible heat engines, there's a clear relationship between heat transferred and temperature. The ratio of heat input to heat output equals the ratio of the temperatures. This gives us a natural, absolute scale. The Kelvin scale comes directly from this logic. It fixes the triple point of water, where solid, liquid, and vapor all coexist, at exactly 273.16 Kelvin. This isn't just a random number, it's anchored in nature, making Kelvin the most fundamental temperature scale for all scientific work.
10. The Carnot heat engine. Let's discuss a simple but powerful takeaway: how we measure the efficiency of the Carnot engine. The Carnot efficiency formula shows that efficiency depends only on temperatures, specifically the high temperature where we get heat and the low temperature where we reject it. The formula is clear. To make an engine more efficient, raise the high temperature or lower the low temperature. That's why power plants use very high-pressure steam, and why refrigerators always try to dump heat to the coolest environment possible. In simple words, hotter sources and cooler sinks make engines better. This explains why there's a limit to efficiency and why energy engineers are always chasing better materials and smarter designs to push these temperatures to the extreme.
11. The Carnot cycle refrigerator and heat pump. Let's look at how the Carnot cycle applies to refrigerators and heat pumps. Both are just engines running in reverse, but how we measure their performance is slightly different. For refrigerators, we use COP, or coefficient of performance, which tells us how much heat we can remove for every unit of work we put in. The smaller the temperature difference between the cold and hot sides, the better the performance. For heat pumps, COP tells us how much heat we can deliver to a warm place per unit of work. Again, a smaller temperature difference means higher COP. This explains why refrigerators and heat pumps work more efficiently in milder climates, and why it's more energy-intensive to cool something to extremely low temperatures. Lower temperature differences always make these systems more effective.
12. Special topic: household refrigerators. Let's wrap up with something close to home: how the second law applies to your kitchen fridge. Modern refrigerators are much more energy efficient than older models because of smarter design. Things like better insulation, more efficient compressors, larger coils, and tight door seals all help reduce energy waste. If you want to save energy, there are simple habits you can follow. Keep the fridge door closed. Every second it's open, heat gets in. Let food cool before storing it to reduce the load. Clean the condenser coils to keep airflow smooth. Don't block the airflow by stuffing things around the fridge. And always set the right temperature, cold enough to preserve food, but not so cold that the compressor has to work overtime. By following these tips, you'll use less electricity and extend your fridge's lifespan, saving energy and money.